Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to debate with you the parallel operation of AC generators. And to do so, I'm bringing this text to help our conversation about the topic. Let me read the text. In today's world, an isolated synchronous generator supplying its own load independently of other generators is very rare. Such a situation is found only in a few out-of-the-way applications such as emergency generators or backup generators. For all usual generator applications, there is more than one generator operating in parallel to supply the power demanded by the loads. An extreme example of this situation is the US power grid, in which thousands of generators share the load on the system. Why are synchronous generators operated in parallel? There are several major advantages to such operation. Number one, several generators can supply a bigger load than one machine by itself. Number two, having many generators increases the reliability of the power system, since the failure of any one of them does not cause a total power loss to the load. And number three, having many generators operating in parallel allows one or more of them to be removed for shutdown and preventive maintenance. Figure 5-26. A generator being paralleled with a running power system. We are going to return to this figure in a minute. Number four, if only one generator is used and it's not operating at near full load, then it will be relatively inefficient. With several smaller machines in parallel, it's possible to operate only a fraction of them. The ones that do operate are operating near full load and thus more efficiently. This section explores the requirements for paralleling AC generators and then looks at the behavior of synchronous generators operated in parallel. Now let's see the conditions required for paralleling. Figure 5-26, this figure here. Let's take a look at figure 5-26. That is one generator feeding a load, and generator 2 is going to come online by the switch S1. Let's see what the text speaks about this figure. Figure 5-26 shows a synchronous generator G1 supplying power to a load, with another generator G2 about to be paralleled with G1 by closing the switch S1. What conditions must be met before the switch can be closed and the two generators connected? This question is very important. Let me highlight it. What conditions must be met before the switch can be closed and the two generators connected? If the switch is closed arbitrarily at some moment, the generators are liable to be severely damaged, and the load may lose power. If the voltages are not exactly the same in each conductor being tied together, there will be a very large current flow when the switch is closed. Okay? Let's highlight it. It is important. If the voltages are not exactly the same in each conductor being tied together, there will be a very large current flow when the switch is closed. To avoid this problem, each of the three phases must have exactly the same voltage magnitude and phase angle and the conductor to which it's connected. So let's highlight it again. To avoid this problem, each of the three phases must have exactly the same voltage magnitude and phase angle as the conductor to which it's connected. In other words, the voltage in phase A must be exactly the same as the voltage in phase A prime, and so forth for phases BB prime and CC prime. To achieve this match, the following paralleling conditions must be met. Number one, let me highlight this. The RMS line voltages of the two generators must be equal. Number two, the two generators must have the same phase sequence. Number three, the phase angles of the two A phases must be equal. The phase angles of the two A phases must be equal. And lastly, number four, the frequency of the new generator, called the oncoming generator, must be slightly higher than the frequency of the running system. These paralleling conditions require some explanation. Let's begin with condition 1. Condition 1 is obvious. In order for two sets of voltages to be identical, they must of course have the same RMS magnitude of voltage. The voltage in phases A and A prime will be completely later we return to these images. Let's continue with the text. The voltage in phases A and A prime will be completely identical at all times if both their magnitudes and their angles are the same, which explains condition 3. Condition 2 ensures that the sequence in which the phase voltages peak in the two generators is the same. If the phase sequence is different, if the phase sequence is different, as shown in figure 5-27A, let's see 5-27A. Here we have ABC sequence. Let's suppose this is the sequence of generator number one. We have generator number one here, and this ABC phase sequence here. Let's suppose it's the phase sequence of generator one. And if generator B is connected in the ACB phase sequence, then their phase sequence will be different. This is what the text is talking about. Here we see that the phase sequence of machine 1 is different from the phase sequence of machine 2. We need to make them equal. They have to match at the time of connection. So let me highlight this. If the phase sequence is different, then even though one pair of voltages, let's say the A phases, are in phase, the other two pairs of voltages are 120 degrees out of phase. So, what is the conclusion? Do not connect them under these conditions. You are going to damage the generators, both of them. Let's continue with the text. If the generators were connected in this manner, there would be no problem with phase A, but huge currents would flow in phases B and C, damaging both machines. To correct a phase sequence problem, simply swap the connections on any two of the three phases on one of the machines. If the frequencies of the generators are not very nearly equal when they are connected together, large power transients will occur until the generators stabilize at a common frequency. The frequencies of the two machines must be very nearly equal, but they cannot be exactly equal. So, when talking about frequencies, there is a little detail about this. The voltages have to be equal and in the same phase sequence. However, the frequencies have to be slightly different, not exactly equal, and the text will explain why. They must differ by a small amount so that the phase angles of the oncoming machine will change slowly with respect to the phase angles of the running system. Okay, they may not be exactly in the same frequency, because if they are in the same frequency, the phase angles of the oncoming machine will not change with respect to the running machine. So the phase sequence, the frequency of the oncoming machine have to be slightly higher, so they will change slowly, but they will change with respect to the running system. And at the exact moment they match, okay, they match, the voltages correspond to each other, then you connect them. at exact the moment you connect the two machines. So the book says they must differ by a small amount so that the phase angles of the oncoming machine will change slowly with respect to the phase angles of the running system. In that way, the angles between the voltages can be observed by a switch, and the switch can be closed when the systems are exactly in phase. So when the two systems, the running system and the oncoming machine, when they are exactly in phase, okay, the oncoming machine will have a higher frequency, so the voltages can slide through each other, okay? And when they match exactly, when they are exactly in phase, then you close the switch and then you have successfully paralleled the generators. Okay, let's discuss a little bit more. I'm going to read the text. These things that we were debating here are better visualized with the aid of an oscilloscope, because with an oscilloscope you can see the voltages passing through each other. If you make the voltage of the system stay still and the voltage of the oncoming generator with a slightly higher frequency connected to the oscilloscope, you're going to see that the voltage waves pass very slowly. They pass through each other. At the exact time they correspond, they are exactly on top of each other, then you connect the switch and then the system will be successfully paralleled. The general procedure for paralleling generators. Suppose that generator D2 is to be connected to the running system shown in figure 5-27. Let's see. Where is it? Oh, here, 5-27. This is what the book is talking about. The following steps should be taken to accomplish the paralleling. First, using voltmeters, the field current of the oncoming generator should be adjusted until its terminal voltage is equal to the line voltage of the running system. So this is condition number 1. Second, the phase sequence of the oncoming generator must be compared to the phase sequence of the running system. The phase sequence can be checked in a number of different ways. One way is to alternately connect a small induction motor. Okay, the book is advising us to use an induction motor, a small induction motor, to the terminals of each of the two generators, one at a time. You connect the induction motor to one generator, and then you connect the induction motor to the other generator. If the motor rotates in the same direction each time, then the phase sequence is the same for both generators. However, If the motor rotates in opposite directions, then the phase sequences differ. They have different phase sequences. And two of the conductors of the incoming generator must be reversed. Okay? Let's understand this. You have both systems, the system connected to the first generator and the system connected to the second generator. You connect a small induction motor to the system, and you observe the shaft. If the motor rotates in the same direction when connected to both systems, then they are in phase. They have the same phase sequence. But if the motor rotates in different directions, you connect to one system, the motor rotates to one direction, let's say clockwise, and you connect the motor to the other generator, and then it rotates counterclockwise, then you know that they have different phase sequences. What you need to do is to simply swap cables to adjust the phases. Another way to check the phase sequence is the three light bulb method. In this approach, three light bulbs are stretched across the open terminals of the switch connecting the generator to the system as shown in figure B. Let's see figure B. Here, take a look at this. There are three light bulbs. See, observe carefully. The switch is open. The switch is open. The generators are not connected. The generators are not connected. The switch is open. But we are using three light bulbs between generator 2 and generator 1 to see if the phase sequences match. As the phase changes between the two systems, the light bulbs first get bright, large phase difference, and then get dim, small phase difference. If all three bulbs get bright and dark together, okay, let's highlight this. If all three bulbs get bright and dark together, then the system have the same phase sequence. Nevertheless, if the bulbs brighter in succession, not together, then the system have the opposite phase sequence, and one of the sequences must be reversed. Next, the frequency of the oncoming generator is adjusted to be slightly higher than the frequency of the running system. For that reason, why this? If you have not yet understood, I'm going to explain it again. Why? The frequency of the oncoming generator is adjusted to be just slightly higher than the frequency of the running system. Why? Because imagine an oscilloscope screen, and you have phase A of generator 1 and you have phase A of generator 2. They will be out of phase. They will be out of phase. Okay? If they have the same frequency, they will never get close to each other. They will never match. They will never reach peak together. Okay? They will never pass through 0, reach peace, and return to 0 and reach the negative peak together. Phase A of generator 1 will reach peak at a certain moment and go to 0 at a certain moment and reach negative peak at a certain moment. And phase A of generator B will pass through 0 at a certain moment, reach peak at a certain moment, and reach negative peak at a certain moment. For them to pass through 0, reach the positive peak together, reach 0 again together, and reach the negative peak together, one of the generators have to have a frequency slightly higher than the frequency of the running system. And when one wave passes through the other, exactly the same, one wave passes through the other and they reach peak and 0 together, then you are going to close the switch. Okay, let's continue with the text. This is done first by watching a frequency meter until the frequencies are closed and then by observing changes in phase between the systems. The oncoming generator is adjusted to a slightly higher frequency so that when it is connected, it will come on the line supplying power as a generator instead of consuming it as a motor would. This point will be explained later. Okay, the text says that it will explain with greater detail later. Once the frequencies are very nearly equal, the voltages in the two systems will change phase with respect to each other very slowly. This is what I was attempting to explain. With the aid of an oscilloscope, you can set the phase A of generator 1 still, and you are going to see with respect to phase A of generator 1, phase A of generator 2, slowly sliding through it, okay? And exactly at the moment they correspond, they are on top of each other, we close the switch and then we have successfully paralleled the generators. The phase changes are observed, and when the phase angles are equal, the switch connecting the two systems together is shut. How can one tell when the two systems are finally in phase? Let's highlight this question here. It is important. How can one tell when the two systems are finally in phase? A simple way is to watch the three light bulbs described above in connection with the discussion of phase sequence. When the three light bulbs all go out, the voltage difference across them is zero, and then the systems are in phase. Okay, very good explanation the book gave us. Okay, let's debate about this explanation here. When there is light in the light bulbs, it means there is a voltage drop between the cables connected to generator 1 and the cables connected to generator 2. Okay? The light is only on when there is a voltage drop. And when there is no voltage drop, when the voltages match, when there is no voltage difference, then the light bulb will be turned off. Okay, the light will be turned off. So when the light is off, there is no light, then you know that there is no voltage drop between the cables of generator 1 and the cables of generator 2. This means that exactly this point you can connect the two generators. You cannot connect them when the lights are on. only at the moment and precisely at the moment when the lights are out. This simple scheme works, but it is not very accurate. A better approach is to employ a synchronous. A synchronoscope is a meter that measures the difference in phase angle between the A phases of the two systems. The face of a synchronoscope is shown in figure 5-28. Let's see. Okay, here it goes. Figure 5-28. The dial shows the phase difference between the two A phases, with 0 meaning in phase at the top and 180 degrees at the bottom. Since the frequencies of the two systems are slightly different, the phase angle of the meter changes slowly. If the oncoming generator or system is faster than the running system, the desired situation, then the phase angle advances and the synchronoscope needle rotates clockwise. If the oncoming machine is lower, then the needle rotates counterclockwise. When the synchronoscope needle is in the vertical position, the voltages are in phase and the switch can be shot to connect the system. Notice, though, that a synchronoscope checks the relationships on only one phase. It gives no information about phase sequence. In large generators belonging to power systems, this whole process of paralleling a new generator to the line is automated, and a computer does this job. Nevertheless, for smaller generators, though, the operator manually goes through the paralleling steps just described. Okay, my friends, this is what I wanted to debate with you. I hope you guys enjoyed this discussion. The book that I used for this discussion is Electrical Machinery Fundamentals by Stephen Chapman. If you liked the video, give a like to the video so we can make more awesome videos like this. Okay, my friends, goodbye.